Okay, so we are going to jump into a new chapter this week. I already gave you a brief intro as to what the next two chapters, actually, not only this one, but the next two chapters will be about. Uh, we are going to start doing the inference part of statistics, and we're going to start doing some conclusions. This is going to be necessary for your group assignment as well. So as usual, I have to credit the references that I used to create the materials. And before we jump into that, I want to review some important concepts that we have already covered in class, but will be very necessary to understand this next chapter. First, a random variable. Don't get bored of these guys yet. They're going to come up again. So as you all know, a random variable is a function that's assigning a numerical value to any outcome. So when I have my sample space like that, the S over there, all of my possible outcomes, all of my possible measurements, all of my possible data points, instead of denoting them as is, I can denote them numerical in a certain way. And every single random variable that I can define will follow a certain probability distribution. And we have looked at some special random variables that follow a specific probability distribution. Some discrete ones that we've looked at, the Bernoulli one, the Poisson one, the geometric one. We learned a couple of special discrete ones there. Additionally, we also studied some special continuous random variables, such as the exponential one and the normal one. So we can assume safely that whenever we define a random variable, it will, in the background, follow some certain rule, some certain probability distribution. Among those are the ones that we have studied in this class. Up until here, any questions? This is the first concept that you need to be able to grasp to continue on. So I'll give you a short pause in case there are any questions. Okay, 30-second pause. No questions yet? Okay, so all of you knows what a random variable is. The next thing that we want to remember is something that we learned at the very beginning of the semester. So when we are doing a study, we are going to study about a population, a large group of people, a large group of data points. But in reality, it's virtually impossible to actually study every single member of a population. Thus, we need to take a sample. This is what we know as sampling. And through the sample, we can compute, sorry, not infer, we can compute some statistics. What are some statistics that we know? We can compute some statistics such as we can compute the mean, the sample mean. We can also compute, why is my pen acting? We can also compute the variance. And one more thing that we can compute, it's not technically a statistic, but we could also compute the sum of various data points. So say here I have 30 samples, 30 data points in my sample. Say I have 30. And I have, when I'm studying UI students, I took a sample of 30 UI students. And from here, from my 30 data points that I have, I decided to compute three things. I'm going to compute x1 plus x2 up until x30. I can also x1, x2 up until x30 divided by 30. And I can also compute the variance. These are three things, three simple things that I can compute easily from the statistics that I have. 30 is quite manageable. 30,000 is not. So from these three statistics that I could compute, these three, the sum, the sample mean, and the variance, it does not mean much to me if they are in their current form. In their current form, they are a representative of the sample, but not necessarily a representative of the population itself. So I could say the mean height of my sample is 154 centimeters. But that does not give me any information about the population itself, the complete UI students. So thus, right now, what we want to do is make these inferences about the population using those samples. So this is our task. What I do have is, hello pen. What I do have is sample mean, sum of x's, and variance. I have these, but how can I use these to infer something about my population? So in order to do so, we need to establish some basic assumptions because this is, as mentioned, an estimate, an approximation. It's not an exact computation. So some assumptions that we have are as follows. So when I'm talking about, just to clear it up, I'm going to redraw a small version of the previous graph. So this is my population and this is my sample. So I have to assume that the population's parameters, so in the population parameters, I have the population mean, I have the variance, and I have the sum of all data as well. So I have to assume that there is an underlying probability distribution of these three parameters. I don't know what it is. In the previous slide, I think it was denoted as F. So I know that every single one of these points has a probability distribution. I don't know what it is. It could be Poisson, like we learned. It could be Bernoulli. I don't know yet what it is. It has some sort of probability distribution. So if I know that every single parameter of the population has a probability distribution, if I take out my sample, this is a sample of the population, I take out a small portion of the population, I have a sample here. That means that every measurable value of my sample, my x1, x2, up until x30, since I assumed I took 30 samples, every single one of these measures is an independent random variable with that distribution. I don't know this distribution yet, but I know that all of these samples that I took out from the population, 1, 2, 3 until 30, each and every one of them is an independent random variable that follows the same distribution. Thus, however I choose to take the sample, the randomly selected sample data will also follow the same distribution. So basically what I'm saying is that if I can measure the distribution of the sample, I can thus assume, or I can thus approximate that the population parameters will also follow the same distribution. How so? So as I just mentioned in my assumption, I assume that every sample I take, so when I'm studying UI students, I'm asking Hanifa one thing. How tall are you, Hanifa, for example? That is one sample, X1. Then I go and ask Altaj, hey, how tall are you? I have X2. And every single measurement that I take, every single data point that I take, I can assume it has a common distribution F that was underlying from the population itself. I don't know yet what it is, but I know that every one of these will follow the same one. How can I do that? So if I take these data samples, just now I took X1 from Hanifa, I took X2 from Altaj, maybe I took X3 from Zahran, and so forth until I have N data samples. As I mentioned, from that, I can assume that every one of these are an independent random variable with a distribution F. Now I want to estimate, what is this F? Is it Bernoulli? Is it normal? What is it? in order to deduce that, in order to make that conclusion, I can do it in two ways. First, I can model it as a parametric, how do you say this? A parametric inference problem in which I set up F to be something that is already specified. I don't know yet the parameters, but I have some basic assumptions about it. Or the second one is the non-parametric inference problem in which I don't know anything about F and I admit I don't know anything about F. Obviously, since we're talking about statistics, the second one is quite an ill-posed problem, which has too many unknown variables. So in this class, we are not going to cover the second one. We are not going to cover the non-parametric inference problem, and we are only going to focus on the parametric inference problem with the assumptions that I already showed in a previous slide. The three assumptions that we have are the criteria of F, so that we can estimate F a little bit better. So as a conclusion, what we are trying to do in the task, so-called task that we're doing here is I want to find the probability distributions of sample statistics. In other words, from my sample here, I have the, sum of X, I have the average of X, and I also have the variance of X. Oh, sorry, the variance of the sample, excuse me. And from these three measures, I want to know what distribution does it follow. Maybe, for example, is it N? Maybe is it B? I want to know what distribution it follows. Why? Because then I can assume that the corresponding parameters here, the sum of X, as well as the population mean and the population variance, will then follow the same one. So for example, this is N with some parameters, then I can assume that this one is also N with some parameters and so forth. So from the data samples that we have, what could I actually measure? We already went through this. We have the sample mean X. There's my pen. We have the sample mean X. We have the sample variance. And there is one more, which is the sum of X. In the group, in the book, it does not specify explicitly this sum of X because obviously the mean is just the sum divided by N. So it is included inside the explanation of sample mean. I think it's quite significant for you to try to compute. So we are going to treat it a little bit separately. So there are three things that we are going to compute and we are going to deduce their distribution from. But how, you say? Well, thankfully, we have something called the central limit theorem, which serves as the basis of the inference from the sample to the population. The central limit theorem, which is the basis, is assuming that when I have n data samples, in my previous explanation, I said 30, or maybe 100, or maybe 120, however many data points you have, we already assumed that each of them is an independent RV with a certain distribution, F. I don't know what it is. Maybe I should note here, just in case you guys are confused, this F here is just a variable and it has nothing to do with the F distribution we talked about last week. Here, we already know that we have a parametric inference because I'm already having a lot of assumptions. I assume they're independent. I assume it has an underlying distribution. And according to the central limit theorem, if you are interested for the full derivation, please go to the book by Ross. It has a full derivation of where this theorem comes from. But for the purposes of this class, we're just going to simply use it. The central limit theorem says that if I have a large N, let me note this word for now, a large N. If I have enough data samples, if I have a certain large amount of data samples, if N is large, then the distribution of the sum, you see here, the sum here is approximately normal with, with this, which will follow the normal distribution by these two parameters. So here we know that if each data point that we do have has a certain mean and a certain variance, then if I want to estimate the population distribution of the sum, then I can assume it equals this distribution here. Some important notes that I would like you guys to realize is the first one is large N. So the first criteria that we have is that we need enough samples. The second is the sum of x's is the basis of the central limit theorem. And lastly, we approximate it to be normal. This is based on the central limit theorem, but also based on the common knowledge that most things are normal, are distributed normally. Since most things can be defined with a normal distribution, the issue now comes as what type of normal distribution? Is it this high? Is it this wide? And so forth. And that's what we compute in this part here. So that's the mean, and this is the variance. But note here that it still follows the normal distribution with an N. Obviously, the normal distribution can be very different. There are normal distributions with different means, normal distributions with different variances. But if you recall, we have one standard normal distribution that can be used as the one main rule, so to speak. So instead of using various different normal distributions, let's just convert that into a standard normal variable. As you know, remember when we are doing the z-scores, what we are trying to do is x minus mean divided by standard deviation. So from here, we know that this is the mean and that is the variance. So obviously this is mean, no problem, and mu is the mean. Since this is variance, I need the standard deviation. And the standard deviation is the square root of that. And in other words, the square root of that is, well, it should be something like that. Square root, yes. And we can put that away, but we remain with the square root of n. Since this is already a standard normal variable, follows z, thus we can now compute the probability of the cumulative distribution function based on the same rule that we learned last week. And since it's already z, we can still use the basic standard normal table that we've already known in order for us to compute these probabilities, which is the phi one, which is just the basic standard one that we have used up until now. So next, in order for us to understand it more clearly in context, I'm going to show you an example, and I'm going to give you a short pause of 1 to 2 minutes to read the example and maybe get the explanation that I just gave you in your head a bit and review it so you understand it properly. And if there are any questions here, you can please unmute yourself or put it in the chat. And while you're doing so, you can also write your NPM in the chat box for me to record attendance. Any questions? Let me go through the chat. Maybe there's a question that got buried by all the NPMs. No, I don't believe there is one. So if not, then please try to go through this example. Anyone? Let's try to do this together. Oh, is that a chat? Is that a question? No, it was an NPM. Okay, so I will now start with this example here. So recall that up until now, we've only looked at the central limit theorem. So we know that from the sum of x's in the sample, I can deduce the sum of x's in the population. That's what, if I'm going to recall the small graph here, I have my population and here I have my sample. Among the three statistics that I could compute, at the moment we're only talking about that one because we haven't looked at all the other ones. So let's translate that into this question here. So let me change colors first. This red ink is intimidating. So here, what do we know? We know that there are 25,000 automobile policyholders. So I know that I have at least 25,000 data points. I have 25,000 data points because I have the data of 25,000 people with insurance, these policyholders, and I know how much they claim yearly. So if I denote x as a random variable as the total claim, all claims, and xi is the claim of one person, one policyholder, one person. So if I follow the central limit theorem, I know that x, which is the sum of 25,000 from I equals 1 until 25,000, this sum of the claim of every single person, I know that this sum, based on the central limit theorem, will follow approximately a normal distribution with an mu and standard deviation. Oh, sorry, I think that's correct. And based on my numbers, then I know that it should be something like this. So I already pre-calculated this. So this sum, I know that up until n, it will go up, it will follow a normal distribution and mu and n variance. So since I have 25,000, so I know that the mu should be the previous mu times n, and here is the previous standard deviation. Oh, this is standard deviation, apologies. And thus the variance, oops, the variance will be the square of it. So this is the final distribution that I can deduce about the sum. So remember that from my sample, I have taken the sum, and this sum is what I can conclude follows this normal distribution. So here, I know that the total yearly claim will follow this distribution. And based on the question, I now want to compute what is the probability that X, this sum, will exceed 8.3 million. So I think I've already computed that, I hope. Oh, sorry, 8.3. You can simplify this, but maybe it's better to just write it down. Million should be 10 to the powers of 6. Yes, I think so. And thus I can translate this into the Z distribution by normalizing it or standardizing it. And I do believe, yes, I've already computed it. So here I want to compute the probability that the total yearly claim is higher than this value. So in order to do so, I can convert it into a standard normal distribution minus the mean and divided by the standard deviation. And then I can obtain the Z 3.5, Z larger than 3.5, which can also be computed by Z less than minus 3.51 or 1 minus that I've already done here. Please don't forget the different ways we can compute a normal standard, the normal phi, the normal CDF, and thus I know that it's very, very, very small. It is around 0.00023. So it's very unlikely that the yearly claim of all of these policyholders will exceed 83 million. Pause here. So now, as a brief recap, so we don't forget, from my population, I now have already deduced if I sum up a certain number of samples, what distribution does it follow? That's the first thing that we can deduce. We're going to go on to the other two in a bit. Any questions? Okay, not yet. Let me check the chat in case someone wrote something. No? Okay. If there isn't any, I'll continue. If you remember, the second thing that I said we could compute is the second thing that we can compute. So the first one was the sum based on the central limit theorem. The second thing that we can compute from our samples is the sum divided by n, which equals the sample mean. And that's what we're going to do next. So recall that the sample mean is can be computed like this. It's just the average, right? And if you remember that X will also be a random variable. Why so? Because we already concluded that this is my sample. I have X1, I have X2, I have until Xn. We already assumed that every single one of these samples is a random variable. Thus, this average, which is simply a combination of all of these random variables, will be a random variable as well. We learned this multiple times when we were going through the normal variable material, that a certain combination of different random variables will also result in a random variable. And from this sample mean, we also can compute the expectation and variance. The full derivation of the expectation and variance of the sample mean can be found in your Ross book. So based on this, we can then compute the distribution of the sample mean. It's not very difficult because just now we have already estimated or approximated the distribution of this part, the summing part only, right? We've already done that. So actually what we're doing is just dividing it by n. So based on the central limit theorem and based on statistical observations, when the sample mean x bar is actually always going to be centered about the population mean mu. The only problem is that its spread will become more and more reduced as the sample size increases. So if this line in the middle, this line in the middle, is the actual population mean, not sample mean, but the actual population mean, we can't really compute it exactly, right? Because we can only take samples. But from the sample mean, we know that the sample mean itself, the distribution of the sample mean, will actually be centered at the population mean. So, for example, this graph here, this first one here, this probably is a certain sample mean. This next one is the distribution of another sample mean. And what differs into them is the number of samples that I take. So you can see here that this is consistent with what we've already looked at before. If we have enough samples, if my n is large enough, then I can approximate the population mean better. Because obviously, if I have, this is my population mean, I want to be able to estimate it as tightly as I can, right? So if I have an estimation that is quite wide like this, that's not very desirable because then it can take any value from here to here. And if I happen to take the value from here, then it's very far from the actual population mean. So my ideal case would be to have an estimated distribution as close as possible to the real mean. So if this is the real mean, I want to have a distribution, estimated distribution from samples as close as possible to my real mean. So whatever I estimate in this distribution will not be that far off from the actual population mean. So here you probably already have an inkling. So why don't, so in order to do this, I must take more and more samples. I hope you've already picked up on that. More samples is always going to give you a better estimation. More samples will always give you a better big picture of what's actually happening in the population. So based on the previous rule, we know that the sum of means, sorry, the sum of means, where am I? Sorry, this is the population, this is the sample. We already learned how to approximate the sum of xi. It will follow a certain normal distribution. And next, we have the sample mean. And we now know that based on the central limit theorem, that it will also follow a normal distribution when n is large. And the only issue now here is what are the parameters? Here are the parameters. Once again, we have normal, we have sample size large, and this is the same case of the first case that we talked about, which is sum of x's. Here, we're talking about the sample mean. This is just how did we get this from the previous one? It's once again a combination of normal distributions. We already went through how can we combine different normal distributions. I had a discussion with, who was it yesterday? I forgot. Was it, I think it was Afriza. I had a conversation with Afriza at the end of last week's class. When we have a certain combination of different normal distributions, we'll end up with normal distributions as well with different parameters. And this, in this case, we will end up with this distribution here. Sorry. And from there, we will have some following properties that comes up if we assume that this distribution is correct of the sample mean. This one here, we assume that it is correct. Then we can have we can compute the expectation, and then we can also compute the variance, and we can have a standard normal distribution with minusing. Don't forget, just now it's still normal, not standard normal. So if I want to change it to standard normal, I must convert it with minus mu and the standard deviation, which is the, this is the variance, right? This is the variance. So the standard deviation would be the square root of it, and obviously it's that. And here I'll get z. Any questions? Okay, not yet. So what I would like to emphasize here is that we already looked at three different things. I mentioned, sorry, three different things that we can compute from the sample: the sum of x's, the mean, sample mean, and the sample variance. Right now we are on the sample mean. Although there are three different things, I'd like to emphasize this one especially because this is the one that you will find most often in problems, as well as in problems both in tests as well as in real life. This is arguably the most beneficial statistic that you can compute from samples, and you can use it to infer the most beneficial parameter from the population, which is the mean. Why so? Because we already covered this in descriptive statistics, that the mean can give you, in most cases, unless there are outliers, the mean can give you a very good idea as to where your data will lie. Case in point, so here we have, we know that we have a bunch of workers, and the weights of the workers has a mean of 167. What's this? Kilograms? Maybe this is pounds. I think this question came from the English book, so I hope that's pounds and not kilos. 167, and a standard deviation of 27. So now I have a sample of 36. So my n, so my n is 36. And what's the probability that the sample mean of their weights lies between 163 and 171? So let's do that first one first. I think I actually already did it. Oh, yes, I did. So I'm going to talk about it now. So we already know, based on the central limit theorem, that any sample mean, the sample mean will follow this distribution. This is from the theory that we know. And in this particular case, we know that the weights of the population will have 167 as the population mean, and a standard deviation of 27. So if I were to compute the distribution of the mean, then I need to compute these two parameters. So I compute this and I compute that. And so I know that the mean itself should follow this distribution. The mean itself should follow this distribution. sorry, this distribution. That's the distribution of the mean itself. Since I know the mean now, what I want to know is what's the probability that this mean, this X bar, will fall between 163 and 171. And before I do that, I want to convert it to a standard normal variable, and thus I can compute it by minus mean divided by standard deviation, and so, and using my table, I'll get an estimate 0.62, which is the probability that the mean will actually fall between 163 and 171. And the second one is what happens if I have a bigger sample size. Previously, I only had 36 workers. Now I have 144 workers. What's the probability that it will actually fall between 163 and 171? As you can see here, the probability is a lot higher because I have estimated, I have narrowed down the distribution of sample mean so that it would actually follow 167, not follow, will approximate or get closer to the actual population mean. Okay, I'm going to give you a short pause here to get to maybe think about this a little bit more. And I'm going to drive in my point as to why this is the most important inference among the three. Any questions? Feel free. Okay. So up until now, you've probably seen, oh, this is an example and that's an example. Okay, I know how to compute it, but why do I need to compute it? In what real world case or real world application would I actually need to know the distribution of the samples? So one very close to our real life example that I could think of is statistics on the internet. You've heard of this before, right? 90% of the statistics you see on the internet are made up. This 90%, where did you get it from? Hey, I just made it up. It's made up anyway, right? So if you see something on the internet, if you read something on the internet, assume you have the resources to compute and do sampling. How do you know that whatever someone is writing down on the internet is true? It's almost impossible to know that. So say that I just read just now, just before this class, I read that on an article that said that the average download speed in Indonesia is 40 Mbps. I don't really know the standard deviation, but I'm just gonna assume it's 7. I just made that number up as I want. So in order for me to check the validity, is it really 14, the average download speed? See, it says the average download speed. So this is mean, right? This is the mean. This is the population mean. And I have the standard deviation of 7. And I want to validate that claim. So in order to do so, I take a sample size of 100 people. I'm too lazy to get any more. And I can compute the sample mean. So I want to find this in the population. Is it true? Is it actually true that it's 14? How can I do so? So in order to check that, I take a range 10 to 19, which is around 14, right? So this is the number line. This is 14. I'm going to take a range from 10 to 19, and I want to know what's the probability that my sample mean really does fall between these two numbers. My sample size is 100. This is my mean. This is my standard deviation. And since I know that the sample mean should follow the normal distribution with mu and I think that's it, right? I think that's it. No, the what is squared? I think it's only the top. My bad. So it should follow that. Based on the center limit theorem, I know that the sample mean should follow a normal distribution with these parameters. Let's compute it and see if it's true. So based on my computation, I have, this is my mu, this is my standard deviation of sample, and thus I know that the sample size should follow a normal distribution with these parameters. And thus, when I'm trying to compute, is it possible that my mean does indeed fall between 10 and 19? Let's see, what's the probability it really does fall between these two limits? And you can see here that the probability is very, very high, 0.997 or 99.7%. What does this actually tell us? This tells me that the probability of the download speed being actually being between 10 and 19 is 99%, 7, 99.7%. Very high. Thus, I can conclude that the initial claim that says the average internet speed in Indonesia is 14 Mbps, then maybe this claim is believable. Maybe it's not a made up, what's it called? A made up statistic on the internet. So this can be valid for so many things that you can read on the internet. Instead of you trying to figure it out, you can actually test it using the central limit theorem by taking some samples and seeing if it actually does, the mean actually does fall in the correct range as claimed on the random statistic. Any questions? Okay, if not, then we just have a little bit more. We have one more that we can calculate. But before we do that, I want to ask you one thing that I've mentioned so many times. So previously, when we're talking about mean, I said n has to be large, right? When I was talking about the sum, where is it? The sum. Here, it also says it has to be a large enough n. So we already know that the more sample we have, we can approximate the mean better, or we can approximate the sum of x's better. Whatever it is, whatever parameter we are estimating, it will give us a better estimate if we have more samples. Makes sense, right? But how many is enough? How many do we actually need? So the general rule of thumb based on the book that we are using in this semester, Ross by Ross, it says that you can be confident, you can be relatively sure about your normal approximation if your sample size n is at least 30. Because no matter how non-normal, how not normal the underlying population distribution is, it could be exponential, it could be binomial, I don't know. No matter how different it is from normal, if you have enough samples, then it will approximate a normal shape. And the last point here, in most cases, blah, 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 it means, this point means that since we have determined that we need at least 30 samples, it does not mean that if you only have 15 samples, it will not be normal. It could still be normal, and in most cases, it is. In most cases, the normal approximation will be valid as well, even if you only have 5 samples. But in order for your estimation to be statistically responsible, 30 is the good rule of thumb that you should follow when you are computing these approximations. So lastly, the last one we have from our population. This is our sample. I want to estimate population stuff. But what I have is only the sample stuff. We have already looked at how we can estimate this distribution, how we can estimate that distribution. And in the last one, how can I estimate this distribution? So once again, if one measure, we already assume that every single sample variance, every single sample, sorry, is a random variable. So a combination of these x's, or the sample variance, will also be a random variable, which we know these are some rules that we can take from the sample variance. So the thing is, up until now, we assumed that the sample that I take from this big population is very small compared to the population. So why is this important? It's because the approximation we take, we always say that, okay, then from this, then it should be approximately normal then, right? This can be a safe assumption if we're working from a very small set of data and I want to extrapolate it to a very large population. But if my population is very, very small, then I can't really do that. So when I'm sampling from a finite population, we're going to model the problem differently. So anytime we're talking about a certain characteristic, we can denote it as a yes or no question. Like, so when we're talking about heights, for example, instead of a specific uh, data points like, oh, you are 154 centimeters, you are 170 centimeters. Instead of that, we can we instead denote proportions like, oh, are you over 170 centimeters? Yes. Oh, are you taller than 170 centimeters? No. So here we have a different way to annotate it. We know that there is, if we have n elements, and P is the probability or the proportion of a population that is taller than 170 centimeters, then I know that NP elements are taller than 170 centimeters, and the remaining proportion is not taller than 170 centimeters. So if I declare it that way, I now have an indicator variable, which we already looked at as well at random in the random variable chapter. So it is either 1 or 0, either taller or not. Excuse me. In this case, when we're talking about yes or no questions, remember, what was that? The very first time I tried explaining to you, I recall that I think I used the example as, can you drive a car or not? Are you taller than 170 or not? Do you like K-pop or not? So if you declare these things as a simple yes or no question, remember that this is actually a Bernoulli random variable, either yes or either no. And thus, if I sum it up, so remember initially we had the central limit theorem, which talked about a sum of all of the variables following a normal distribution. But now the sum of it, a sum of a Bernoulli random variable, what's that? If I have multiple yes or no's, like I asked multiple students in this class, can you drive or not? Then a sum of a Bernoulli random variable, if you remember, it is a binomial random variables with the parameters and or if you write it with the different with the correct annotation, sorry, you can write it as a binomial random variable. And following all of the rules of the binomial random variable that we've already studied in discrete random variables, you can then compute the sample mean, what's the proportion of the sample mean, what is the sorry, what is the expectation, and all of the other parameters that we use. So as a brief recap, we have a big population here. I cannot study them all, so instead I take a population. From here, from my sample population, say I have n samples. I got my questionnaire out to 12, n people. From the answers on my questionnaire, I can then compute, hey, I'm going to compute the sum of all of you guys. Oh no, I'm just going to take the average of all of you guys. And I can also compute the sample variance of you guys. Why is this important? If I can deduce what type of distribution you follow, this will give me a good idea as to, oh, how is the sum of all of the population? How is the mean of the entire population? And how is the variance of the entire population? Please keep in mind that if I want to do this, I need an n at least 30, and I need the population to be a lot larger than my sample. In the case that my population is not very larger, it's not always larger than my sample, then instead of approximating these as some sort of normal random variable, instead I need to denote it, instead I need to denote it as a Bernoulli random variable, which we've already studied before. Pause, any questions? It looks very simple if I put it down in this drawing here, but we had a bunch of slides over there in the back. Any questions? Feel free. And since, what time is it right now? It's 2:30. I think we have ample time to briefly continue to the next chapter. So while I prepare that, I'm going to, let's have a short break around 5 minutes, but don't worry, I'm not going anywhere. So if you have any questions, feel free to unmute yourself or put it in the chat box. And you guys can take a short break, go get some more coffee or whatever. And I'll start with the next chapter in around 5 minutes. I hope that's long enough. While you're doing that, feel free to chat or unmute yourself. I'm not leaving. I'm still here. Okay, guys, sorry for the delay. I had a call just now. And are any questions before we continue? Hmm. Let me see where am I? Okay, no questions. Are you sure? Okay then. So the next chapter is also more or less following the same not pattern, but the same principles of the previous chapter that we just talked about. So I'm going to cover all of the possible scenarios. We may not have time to go into every single scenario on their own, but please be ensured that the difference between each scenario is just a different equation. So don't worry so much that if we don't cover it. It's just that if you can identify what case you are currently dealing with, then you can select the correct formula, and that's it. Okay, so this chapter is parameter estimation. So in the previous chapter, what we did is we have a big population which we don't know much about yet, but in order to study it, in order to take some inferences about the entire population, we take a smaller set of data points, which is our sample. And in the last chapter, from the smaller sample that we had, we can compute the sum, the mean, and the variance of the sample. And from that, we can conclude the sum, the mean, and the variance of the population. This is what we did in the previous chapter. So in this chapter, now I don't want to know only the distributions. Now I also want to be able to estimate the actual parameters. So if this sample, so roughly, if I know here, oh, the sample mean here is 154. I want to know what is the population mean. Oh, it's 157, for example. So in this chapter, we are actually going to estimate the values of the parameters themselves. So obviously, you might already deduce that. How can you actually do that? How are you supposed to make a bigger deduction or inference about a big population, a lot more data from a smaller set of data? Just as this is going to be important if you are interested to go into data science or machine learning in the future. This is what you call an ill-posed problem or a underdetermined problem. So you want to estimate something very big with a lot of variables, but you only have a small portion of things that you know. And thus, this is very ill posed, and it's almost impossible to solve the bigger picture without so many assumptions. So let's see what we can do about it. In order to do this to assume to be able to estimate the actual value of mu of the population, then I need to have estimators. And in order to determine the estimators, we can use the maximum likelihood method. Just a sec. So what are these estimators? Let's see what these estimators are. These estimators is what we can actually measure from the sample. What measure do we have? You could, as we already did in the last chapter, I can estimate the sum of x. I can compute the sum of x's. I can also compute the sample mean. Oh, I can also compute the sample variance. These are our estimators. Our estimators is what is an estimator is the actual statistic that you use to estimate the parameter. So you could use the mean, the sample mean. You could use the what's it called, the variance. but don't mix up between estimators and estimate. So for example, if if I'm studying a big population of UI students, the IPK, no, the GPA of UI students, I'm taking a small portion of them. This is my small population. And I want to compute the sample mean of GPA. Oh, it's 3.2, for example. If I ask you what is the estimator, that means the estimator is the sample mean or X bar. What is the estimate? The estimate is the observed value. So in this case, the estimate is 3.2. Please don't mix up these two terms. The estimator is the statistic name, the type of data you take, and the estimate is the actual number, the actual value that you have. So, not first. So what I have here is, so I have my population, I have my sample, and now I have my estimator, which is a certain statistic. Here I took the sample mean, and I have my estimate. Now, using this estimator and estimate, what I'm going to do is I'm going to use this to actually give me the parameter theta using the maximum likelihood estimator. And the type of estimate that I have that I can try to obtain from the population are two types. I can either get a point estimate or an interval estimate. Based on the name, a point estimate will give me a certain point. Oh, I want to estimate the population mean. If I have a point estimate, that means I'm estimating, oh, the population mean is exactly 157. On the other hand, if I want to compute an interval estimate, just like the name, it is an interval. So instead of that, I want to know that, oh, my population mean, probably falls between 150 to 160. So here you know the plus and minuses, obviously. Here I can get an exact estimate, but it will likely be inaccurate because can you imagine how difficult it would be to give an exact estimate? On the other hand, it will be easier for us to be able to compute an interval, a range. This gives us a bit of leeway. It gives us a bit of room for error. So if I say, oh, it's between 150 and 160, then I can be a lot more confident that I could be correct because I have a possibility of 11 values that it could take. So you are going to have a trade-off between accuracy and also confidence. And exactly that, we have what we call a confidence interval. So rather than a point value, in statistics, we commonly specify an interval in which we think the parameter lies. The parameter theta here is just a replacement because we could estimate the variance. We can also estimate the mu. So instead of using these two symbols interchangeably, we're just going to use theta as a replacement. So instead of me saying, I want to estimate the mu to be 150, an exact point, I would just say it's between something and something. Secondly, we also want to determine how large of an interval I want to define, how confident I want to be about my interval estimate. Why so? Because we will never be 100% certain that the interval that I write is actually correct. But if I have a high confidence interval, that means that I will have a high confidence that my interval is correct. So if I say I have confidence of 95%, that means I'm 95% sure that when I say the mu is between 150 and 160, it will 95% of the time be in that correct interval. So what since we're talking about estimating parameters from estimates, obviously it's not like I can take any estimate I want and use it to approximate any parameter I want. Obviously, we have some limitations. So in this course, what we are going to cover is not everything. So what we are going to cover, interval estimates in a nutshell, is as follows. As a brief recap of this chapter, we are going to very ugly circle. I'm so sorry. Let's redo that. Let's try again. So from my big population, this is my big population, I want to take a smaller sample. This is my sample. So from this sample, what can I do from here? If I am taking this sample only from one population, so only one population, I can compute two things. I can compute the mean if the variance is known. I can also compute the mean if the variance is unknown. Oops, sorry. Secondly, if I have two populations, should be separate. Undo, sorry. Where am I? This is population 1. And say this is population 2. So here, if I take a sample from two populations, this is my sample from two populations. So I have population 1 and population 2. I can also compute the difference of the two means if the variances, if variance 1 and variance 2 are known, if variance 1 and variance 2 is known, and the difference between mu1 and mu2, if I don't know them, but I know that they are equal. And lastly, if I have a completely different setup and I have oh, sorry, one thing is very important. I'm really sorry. In these two populations, I have to assume that they both are normal. And lastly, if I have a certain population that follows a Bernoulli population, I can then compute the mean of that. So a better recap is this. So if I have my sample from one normal population, I can compute the confidence interval of the normal mean, the mean of that population with known variance and the mean with unknown variance. Here, if I have two populations, I can compute M1 minus M2 if the variances are known, or if they're not known, but I know at least that they are equal. And lastly, if it's Bernoulli, then I can compute the mean of it. And that is basically all you need to know. You need to be able to distinguish what you are trying to estimate and what information you have. And then you have to then choose the correct equation that you need to use to compute it. I'm going to give you one example, which is if the sample is obtained from a normal population or two normal populations. And then for the rest of it, I'm going to encourage you to look through these slides on your own. And we're going to have a short activity next week for this exercise. So here is the first case. If I know that if I know that the sample is normal and I know that my sample comes from one normal population, then it's only the case is if I know the variance or if I do not know the variance. These are the different confidence intervals that I could compute. So here, what is the alpha? This is my confidence level. Is my confidence level, if this is an alpha of 5%, that means I am 101 minus 5%, oops, 0.05. So that means I'm 95% confident that my interval will contain the correct parameter. So in order to do so, I can either have a two-sided confidence interval. That means that, oh, I know that my parameter will be between this value and that value. Or on a one-sided upper CI, I know that it will be higher than this, but I don't know when it will end. Or it can be, oh, it's lower than this, but I don't know when it starts. Obviously, this will probably not be very accurate, but easier to compute, these two. But this one will be a little bit bigger pain in the ass to compute, but you will get a better estimate because you have two limits, left and right. So for an example, we have this example here. I'm going to give you a chance to read through it before we go on. So I'll give you around 1 minute to read through it. Okay, so from this data, we are going to use the previous equations to construct the confidence interval. So this is very messy. Let's delete this. So using these values, I'm going to compute the intervals. So here I want to construct the confidence interval for mu. In other words, I want to define the interval, the limits in which I believe the mu to be. So the population mean should fall between this interval that I define. So in order to compute it, what do we need to know? We need to know, see, we have Z alpha, and we also have the sample mean, and we also have, oh, remember this? We already saw this before. This is the sample variance. So here, in order for me to compute that, I first need to be able to compute the sample X. How to do that? I have all these values. I need to sum them up, divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. I believe that the sum is already computed. I think the sum is 81 divided by 9. So I know that this is 9. And thus I can compute, oh, it's already computed here. So the sample mean is 9. And the sigma is already known. Don't forget that what we're currently talking about is estimating the normal mean when variance is known. So the variance is given in the question, I think. Yes, the variance is indeed given in the problem. So we know that the variance is known. And thus, if I plug in all of these values in the 95% two-sided CI, what does it mean two-sided? I have limits on the left and at the end. So here we have the left limit and the right limit. On the one-sided upper, that means I only have the left limit. On the 95% lower, it means it only has the upper limit. Note that the upper here is not the same as the upper there, because if you recall from the equation, here the alpha is divided by 2, because when I'm talking about a normal distribution, when I have a two-sided CI and my alpha is 0.05, then I need to cut off the interval on this side and that side, and thus my alpha will change. Here will be 0.025, here will be 0.025. Whereas when I'm only using it one limit, then I'm only cutting it off here. And this alpha, if you remember, alpha is the proportion under the graph. So here it's 0.05. That means that every time I compute a limit, it will be different from left and right. So based on that equation, the equations of this particular case, I can define the two-sided CI. Note that if I have a bigger alpha, so if I have alpha equals 0.1, for example, so you can see here that if I have 0.1, it'll be a little larger, right? It'll be here, right? My limit. So this will be 0.1. And thus, here it also be 0.05. This will be only 0.05. Note that when I have a larger alpha, I will have a smaller interval, which gives me a more precise, accurate, sorry, not accurate, a more precise estimate. But the confidence will go down. So my confidence is the opposite. So when I have an alpha of 0.05, that means my confidence is, based on this one, 100 minus 1 minus 0.05, which is 95%. But if I have alpha 0.1, that means my confidence is 90%. So as you see, the smaller my interval gets, the less confident I am of my estimate. That makes a lot of sense because the more I'm narrowing it down, that means that I could be wrong because it could fall out of the interval. So this is a trade-off that you must consider when you're trying to estimate this. Do you want a more confident estimate, which is larger, or a more precise one, but you could be wrong sometimes. So this is the first case, normal mean when variance is known. You can also compute when variance is unknown. This is the equation. Note that the biggest difference here is that we are no longer using the Z table, but we are using the T table. That is the only difference. The equation is exactly the same, but the T values are used instead of the Z values. You might recall that the biggest reason is T is a variation of normal, but you don't know the variance, which is exactly what we have in this case. We don't know the variance, so we cannot use the standard. You can check the equation here, and this is the variance, so you can compute the variance as well. The second case, when we have two normal populations, we can compute the confidence interval of the difference in mean, so mu1 minus mu2. As such, if you have the variance, you can compute it using this equation. There's an example here, which you can compute as follows. Or if you do not know the variances, but you know that they are equal, once again, we don't know the variances. We cannot use the Z distribution, but instead we can use the T distribution. Okay, the formatting got messed up here. My apologies. I'll fix that and re-upload the slides. And we can compute the differences of that here. And finally, the last estimate is if we do not have a normal one, but instead we have a Bernoulli distribution. And thus we can estimate it using an estimation of binomial NP. And here gives the confidence interval of the mean Bernoulli. Okay, so I'm not going to go into more detail of every single case that we have today. We can review it through an exercise and maybe we'll go back into it in more detail next week. But I hope that this summary here will give you a general idea as to what you will be able to do in this chapter. So what type of sample do you have? What type of estimate do you take? What sample statistic you take? And you can use it to estimate the parameters of the population. Obviously, you cannot estimate anything using everything using anything, sorry. So these are the limitations that we are able to compute and we are going to cover in this. Any questions? Oh, I muted. Sorry, I didn't realize that. Any questions, anyone? So as a brief reminder, this last chapter that we went through very quickly, we haven't gone into every single case in detail, but I do hope you get the gist of it, of what we're trying to compute. And I will release an exercise next week in order for you to get more familiar about it. And once again, I want to reiterate the announcements that I started the class with about your midterm scores, the opportunity for resit for some select students. Please check your UE email account. The group assignment, which has already been released and you can already start working on it. I highly recommend you to start distributing your questionnaires because you will need time to process them. And finally, we will have an exercise to accompany this material next week before we go into the hypothesis. Any questions? Go ahead.